Eugene Fratkin has a Stanford PhD in machine learning. He has built ML systems for cancer diagnostics. He has led engineering teams at Scale AI, Clari, and now at Salesforce. Today, he's going to walk us through why ML projects fail, how can we evaluate ML projects, how can we scope it so it's buildable, and how can we refine the data before you build on top of it. I'm Suresh Mathew. This is One Idea. Please take a moment to subscribe. It takes 5 seconds. Welcome to the show, Eugene.
Thank you.
So before joining Salesforce, you were at a startup that you founded building cancer diagnostics ML systems. I'm sure there were a lot of constraints associated with it. Tell us a bit more about the constraints, how you built that ML system. What was your strategy in making sure that those constraints are met?
I think that most people think about regulatory constraints when they think about diagnostic, and absolutely you have to make sure there's a validation plan, there's College of American Pathology that reviews it, you have to be certified, etc. This wasn't the biggest obstacle. Biggest obstacle we ran into is lack of taxonomy, lack of the data that you can use to run your automated diagnostics. For instance, at the time they had 60 different taxonomies of cancer, but none of them were meaningful enough for the type of automated diagnostics product that we're building. They were conflating stages of the tumor, tissues, genomic composition, and we needed genomic and kind of relevant biomarkers that we're looking at. So we had to start by recreating all of this data from scratch, making sure it's clear, it works well in automated product. This was actually a bigger obstacle than a lot of regulatory constraint of what people commonly think of.
When you joined Clari, the ML team there had been running for years and had a suboptimal output. What was the root cause or the source of this inefficiency? How did you go about fixing it?
I think that's kind of when you join as a VP, usually there are some things that companies trying to make more efficient. That's kind of nature of the job. Usually there is a playbook how you navigate. And with machine learning, honestly, the same playbook works very well. Typically, people invest into algorithmic side and they underestimate the fundamental investment into the architecture necessary to support machine learning efforts. Not machine learning architecture, software, data engineering pipelines, experimentation framework.
The hard ones.
Exactly.
Not so interesting ones.
Not the sexy one. And there is almost like a quantum of minimum investment you need to make into machine learning before you actually start producing interesting machine learning. And it's very commonly overlooked. People focus on the algorithmic side, and a lot of this becomes very inefficient, especially if you approach it the way you do software engineering project, where it's reasonable to have design in mind, and then you go about executing this design, and it may take several months to kind of come up with a viable product. In the machine learning world, even if I have very good hypothesis, it can absolutely fail, and you have to be prepared for this. So you need to be able to test hypotheses very quickly to the point where kind of financially, sentimentally, etc., from corporate outlook, it doesn't look damning if the approach fails. So having this flywheel working fast is super critical.
So basically, fail fast.
Fail fast and fail often.
And also, I'm thinking one other aspect would be make sure it's measurable. You can evaluate it quickly.
Yeah, absolutely.
And you had a framework called MSOS in Clari that really helped you. In fact, the project was really sales call to transcription to feature extraction to really model. How do you make sure that you can test it, you can validate it at every step, unlike software engineering?
Philosophically, it's similar. Practically, for the same reason that I mentioned earlier, people tend to forget about everything that leads up to the modeling aspect, and they spend a lot of time optimizing the model. And when there is a failure, they assume it's a model that's failing. Probably more time than not, in my experience, it's not the algorithmic part in the model. It's data leading up to it. Either it's too noisy, not representative of the current data flowing through the system. We had the experience in Clari where we had a system that was working very well offline in experimental setting. And then when we try to measure it in dark deploy mode in production, dramatically worse results. So it turns out that the data that we accumulated, we were using for testing, sounded very plausible was collected in a reasonable way, but did not represent the real data. So you have to be prepared for that and know that this is one of the common failure modes.
And how do you recover?
Well, once you identify it, typically there is a step to, so the problem known as alignment, right? Generically in machine learning, where I'm developing a model, does this model behavior aligns with the actual problem I'm trying to solve? The same goes with data. Like, is my data a good proxy? Data used for offline for R&D is the good proxy to what I'm going to see in production. And sometimes you get it wrong. Again, it's not a human failure. It's this experimentation piece that I was talking about, that you should always assume that experiment can fail, and this will happen often. And in fact, I measure effectiveness of the team of how many things they tried that didn't work.
That probably tells you what is the level of tolerance, one, for failures, and second, for the research aspect itself, right? So you cannot build something new without.
Precisely. So if team tells me that nothing failed, everything that they worked on has shipped as they anticipated, either they're being unambitious, they're not taking risks, and that means that they probably will not produce anything innovative, or they're moving super slow, super cautiously. And I do not think that machine learning team that moves slowly will exist long term. It's an expensive piece, and it needs to be able to move fast to provide sufficient value.
You're absolutely right. If you're not moving fast enough, if you're not failing fast enough and recovering fast enough, chances are slim for you to succeed in this current world. Google's paper argues that 7% of the work is in the model code, but the teams are not realizing it well enough now. Now, how do you really expect the industry to acknowledge this and focus on the whole shebang of things and not just focus on the model?
Yeah, there was a paper that I think goes back to
2015,
2015.
yes.
Yeah. Hidden technical data machine learning. So one of my PhD classmates was on a paper, and I think it's still very relevant because it shows how little machine learning is in machine learning project. And yeah, it's absolutely correct. And I think that again, when you constructing viable machine learning team, you want to make sure there is sufficient supporting team around it that's able to provide that.
There are other aspects, like data pipeline is one, right? Validation frameworks are another. Making sure that you have enough data quality when you start building the model is the third, right? So how do you make sure that everything comes together? How do you make sure that teams understand that this is how the distribution should be so they get the right outcome from that?
I mean, it really depends on the team. There are people who have been working this mode for a while. They know what correct setup looks like, what you need to worry about at which stage, etc. That none of it needs to be said. But I think there are kind of two specific different failure modes that you see pretty often. You see classical machine learning, not classical, sorry. You see machine learning people who do not have a lot of industry development experience, who tends to over index on kind of interesting machine learning research and experiment there. Even worse, people start working on new machine learning methods, and there's absolutely room for innovation, new methodology, in some very, very special teams, either in universities or large companies. For most product companies, you would have to provide very convincing argument how nothing in the universe of machine learning research works for you, that you need to develop your own methodology. Yes, this is one thing to guard against. On the other extreme, if you have software engineers getting into machine learning, they tend to treat machine learning as a black box, and they shy away from anything except for basic prompting. Like, I would definitely not encourage people to invest into very heavy, complicated things until you exhausted the simple stuff. But you shouldn't be shy to use it when necessary either. And I've seen classical software engineering teams that just would not go deeper than a superficial route. So yeah, both of those are extremes. Obviously, there's everything in between. And there are people who have been doing it long enough that this is not even a complicated conversation. They know exactly how to have it set up.
Or maybe have the right mix in the team itself, right? Some people who are ready to jump deep into it.
Yeah.
Yeah, got it. All right, now about how to validate things, right? Even in OpenAI, you've heard that 60% of the time, even the deep researchers, they don't have concordance on what is the right result, right? So how do you advise or suggest that teams handle it?
Yeah, that's by the way, kind of fantastic example, and also worked with OpenAI at Scale AI. Definitely humans have strong intuition, and sometimes this intuition appears very strong, but when you quantitatively validate it, people disagree on things they thought that they are on the same page about. So yes, definitely validation is one thing. So typically I'd like to establish kind of upper bound, lower bound on quality. Depending on the project, it could be more or less complicated, but usually it's feasible. I want to know what's a base level thing. If I do the dumbest heuristic, what is the quality I get? And if I'm not improving on top of that, then there is no reason to do something much more complicated. At the same time, given the noise in the data, given uncertainty of the task, etc., what's absolute best? If I try to remove every uncertainty feasible, what is the absolute best answer I can get? And this is my upper bound. And sometimes upper bound is not that high. You will not get 100% quality. Sometimes the upper bound is 65. And it's very important to know, because if I'm at 59, 58% quality and my upper bound is 65, if I have perfect knowledge, I know I'm doing pretty well. Cannot really improve significantly.
So knowing that bound is probably the most critical thing here.
As you're executing project, basically with machine learning project, every project has a research component. So there is always a question: are we done? Should we invest more? Should it be better, etc.? So typically you want to design a metric that you're tracking and you're seeing whether it's improving or not, using a little bit of judgment how quickly you expect it to happen. But the bound should play a very important role in this determination. If you know you're not just plateauing randomly, you're plateauing because you're hitting some feasible limit, then you should know that you gotten as far as methodology could possibly take you.
A very common stressed saying now: data is the new oil. And you have said that there are a lot of oil-rich, poor companies.
Yes.
Please help us.
I think that this became a general wisdom that models are very data hungry, and the more data you have, this is kind of intrinsically super valuable. I'm not going to question this assumption wholesale. There are cases where indeed this is the case, but you have to go a little bit deeper than that. When I work with new companies, where I join a company and people tell me that they have amazing data, typically, there are a few things to analyze. First of all, how much of this data is consistent, generated using the same methodology? Is it still historically relevant? Does it address all of the questions you need to build the product you're working on? Typically, it turns out that there is much less valuable data than you expect. Like if, let's say, I want to work on salesperson, people efficiency. I want to understand what makes sales successful or not. There is conversational part, there is estimates, how many end-to-end journeys do I have from initial call to closing the deal? I have all of those pieces in place. If it's partially there, it's up to you to determine to what degree it cripples your effort. Autonomous driving is an interesting example because companies initially spend a lot of time, money, resources on generating basically data just driving down the streets using LiDAR and sensors to create a sensor fusion of scenery they're observing. And for a while, this was super valuable until kind of everybody knows how to drive down a normal street. And then you're only interested in very special events with disengagements where a human takes over, and you're only interested in how many events like that you have in your ontology. And then that changes, and turns out that it takes 4 million miles to encounter a single disengagement. So it's no longer viable to even drive around. So you start looking for synthetic ways to generate these scenarios. So a lot of data that was valuable at some point becomes really, really not that interesting later down the road.
Because it's the same. Yeah. I think that is a precise number in the autonomous vehicle world. It's like 4 million miles for a disengagement, correct?
It was true at some point. I do not know what it is this year, but definitely it's something like this. We see autonomous vehicle driving on the streets. They do not encounter a lot of disengagement events.
Otherwise, we'll read it in the newspaper.
Yes.
Slightly off topic, right? So the expense of using LLMs in engineering world. Cost was a huge concern back then. Maybe 2 years ago, it was like $180 for a million token. Now it's probably 75 cents, right? So it has come down. Now, do you expect this engineering teams to carve out a budget maybe equal to or even more than the resource spent for the same team, human resource spent?
Experimentally, we do not see a lot of teams that spending so many tokens that it would come close to human salary compensation at the moment. Not know if this is a temporary limitations Ultimately, you may have a single person working with 50 different agents that running a lot of experiments through distributed system and kind of tokens going through the roof. I don't think we're quite there yet. Also, token prices keep dropping.
It just keep, yeah.
So I'm not sure that we'll ever be there. At this point, the budget is probably a little bit more than discretionary, but usually it's not that expensive to enable every engineer to use pretty much as many tokens as they need to.
180 to 0.75 is like significantly lower. It's now almost, unless you have uncontrolled looping expenses, right? If there's a leak, then that's a problem. Otherwise, it's good.
If we're talking about purely for software development or engineers, or are you talking about in a product and using it as a part of the feature?
There are a few ways I've seen companies using it. For us, we have some agents debugging things, so people are not really looking at it at all times, right? There are cases where we have written some agents that can even coordinate with the rest of the agents too, right? So those cases, they spend tokens. But I don't think a lot of large companies are experimenting it that way. For us startups, we can afford to really do some of these. But I believe they are all marching there pretty quickly. So I see people using very sophisticated coordination, very sophisticated graphs for machine learning agents, right? So if that happens, I think there will be some more spent than what we see today.
Yeah, so definitely spending is increasing, and I think it's becoming easier and easier to justify because there is output that's growing. I don't think we're at the end of the learning curve. I don't think too many people can claim that they understand what efficiency means with running software engineering company fully AI native, both in code development, monitoring, etc. But like justification for the money being spent right now is not very complicated to come by. We see it quantitatively. Salesforce experimenting a lot with different models, and the one result that's very clear, it is paying off.
Yes, absolutely.
Question is, can you make it 5 times more efficient? Maybe. I'm pretty optimistic in terms of we're nowhere near plateau in terms of efficiency of technology. So I think we're all on a learning curve. There are different hypotheses. I have mine. Other people think.
Yeah, it's changing. I agree with you. The only thing we can tell people now is like be ready to for and be the change agent. Right? That probably is the easiest. Now, the things that we discussed so far, right? Does it apply to probabilistic models only, or does it apply to the non-probabilistic? Just say linear regressions, right? So statistical models, right? Does it apply to everyone or everything?
I would say it applies to anything. Obviously, it's a little bit easier to analytically predict how regression is going to behave than kind of large language model. So level of uncertainty, number of guardrails, probably you can reason a little bit more analytically in world of classical machine learning. But I don't think it fundamentally changes the equation. I still do not know in most cases how effective the statistical inference is going to be, how much lift I'm going to get. So generally the same things apply. Maybe there is a question on how much weight I put on this and that project versus the other one.
And by the time you left Clari, there were 700 customers successfully running on the platform. So for a person who is trying to take on that role, right, going to lead that such a team, what would be the first few steps that one has to take?
Yeah, so this was specifically a data platform, right? So in some sense, data platforms in my mind exist in like almost the opposite world from machine learning, where data platform, you have to worry a lot about consistency. There are no quick wins with data platforms. It has to be very deliberate, very careful. Data loss and restoration are very time consuming, expensive, difficult to manage with customer if it happens. So typically you want to be very, very careful and methodic. Versus in machine learning, I'm advertising literally the opposite model, right? Until it becomes mission critical, like move fast, get feedback, determine what the true value is. Then you double down when kind of all of the questions answered. That's when you start making it harder and kind of implement it in more cost-effective way. Do not optimize to your.
So measure and optimize it as, or take the optimization as late as you can. For engineering leaders specifically, for people who are building systems that use ML models, there are multiple teams that can fail, right? So it can be at the machine learning model itself, or the machine learning team, the platform team, or the consumer team, the people who are calling those APIs. And what I've seen, at least in our cases, is like these interactions are extremely important. and you get the feedback to each other pretty quickly. What is your opinion on how to build this together?
Yeah, I mean, you kind of have an answer in the question where it doesn't work very well when you view them as truly separate teams, where I have application team that defines my requirements. Those requirements land on the machine learning team. By the way, I would extend it to the product team. They all need to be part of ideation together. They all need to be part of brainstorming. They need to understand each other objectives, even though I'm not coding the front-end user experience. I need to understand what ultimately user will see, how they're going to interact with the product. It helps me to define the machine learning problem more precisely and also spot failure modes, anticipate them during the development process.
What are the top 3 things that was like, man, it was extremely difficult, but I'm happy that I learned it and I will not make this mistake again? And what are the things that you would say, like us as startups, right? We should never be doing.
So I came from a technical background, and technical people like to work on technical problems. They tend to shortchange the go-to-market side. And go-to-market, especially in the industries which are pretty slow-moving, very conservative, like medical industry, is very important. And one of the things that happened to us, which was both fortunate but interesting learning example, Mayo Clinic was our investor and co-development partner. And me not being a medical professional, we work very closely to understand their needs, their view of the market. Mayo Clinic is not a typical clinic. It's one of the centers of excellence. So they will have 19 doctors in a concilium thinking about what is the optimal regimen to treat this patient. This is not how most community clinics work. And I think that gap that we discovered when we started actually going to community clinics and selling the product was pretty dramatic. Typically, those people in centers like Mayo Clinic, Sarah Cannon, you can think of them as researchers. They aware of all of the ongoing research. They may need the latest information about ongoing clinical trial, but they do not need to be given refresher course on kind of new trends and cancer treatments. For community clinic doctors, they cannot keep up with 100,000 publications a year on cancer treatments. They would very much like a refresher to understand those are the important trends for you to be aware of. So we had to pivot product quite a bit to kind of simplify and take him on a journey. We couldn't just tell him, here's the interesting results. Hopefully you know why we're giving it to you.
Basically, the design partner that you had was very sophisticated, and the customer or the wider audience were not able to take it.
Correct. Yeah. They needed to be taken on a journey. They needed a little bit help to understand why it's relevant to this patient. How does it compare to the standard of treatment that they're aware of, etc. That was number one example. Number two, we talked about it a little bit. Quality of data was very paramount. And I think heterogeneity of what we saw both in dealing with clinical data that we're getting from patient samples, as well as lack of clean ontologies, was really something that we initially understated. And it became very obvious when we started benchmarking and trying to.
What did you eventually do?
So initially we were assuming it's going to be completely in silico computational product. So we're taking patient samples, doing genomic sequencing, doing secondary analysis, assembling DNA, determining what are the mutations that we're observing, and then doing natural language processing to find literature, find clinical trials, and determine is there a match between the trial and specific presentation we see from the patient. We realized that both for reimbursement purposes, you have to have the whole pipeline, including clinical processing of the sample. So we had to build out physical lab with doctors doing the processing. As well, we had to build out ontologies. It was not obvious to me coming from academic background that out of 60 clinical ontologies that exist, none will be suitable for our product. And actually, this is a pretty common in life sciences because I think still not a lot of it is completely computationally processed. So a lot of them still rely on the human intuition. And we understand this is like not exactly the right ontology, but I know what you mean by this. Once you feed it into the computer and try to run it as a decision tree, you remove this human factor. So it has to be precisely correct, and all of the assumptions need to be well understood by the system.
So the end of the day, so for such a good cause or great cause, that kind of an extra step or extra mile makes a lot of sense, right? Especially for that sad research. That kind of research, I think going that extra mile makes a lot of sense.
Yeah, there's a lot of small, interesting examples that happen. And kind of when you look at life sciences literature, you see mutations that are appear there's a certain way how you call mutations, depending on the model, if it's a human, if it's a mouse. So you find some accidental mouse notation within papers discussing human pathologies. So it's pretty critical to spot it and understand that, no. I know you experimented on the mouse, so you're using this notation. This is not actually in human. In human, it's a different gene, different whatever.
Is this, when you say annotation, I'm just, since I'm not very familiar with that field, is it like the annotation in the software world? That's what we're talking about, or?
Yeah, you're saying that in this protein, in this position, I see substitution of this letter to this letter. And you're looking at a human, you're like, humans do not have this letter in this position. You're thinking of mouse.
It's not, again, just a decorative change, right? This is a significant difference.
Yeah, it's typically it doesn't lead to incorrect treatments because it's kind of the opposite. You make sure that you understand the mutation, but it does mean that sometimes you filter out relevant signals because you don't recognize, does not make sense. So, like, we're dropping it, probably irrelevant polymorphism.
At least no dangerous outcome, but it's still irrelevant outcome. Perfect. Thank you, Eugene, for coming and talking us about your journey here. Thanks, everyone, for watching. I started this show because I believe engineers deserve better guidance than just generic conference talks. If there is one thing that was valuable to you as a takeaway from this podcast, please subscribe. It takes 5 seconds. That's a good indication for us to continue bringing such hosts and talking and discussing these things. These guys have seen this at scale, failed at scale, have learned it the hard way, and they are here to share those lessons in a crisp fashion to you. Thank you.